So looking at a couple of examples on two population t-test problems. Here's the first one. The manager of a large production facility believes that these two designs may differ in the amount of time it takes to assemble them. So we've got some data that we can go through here. And one of the things I like to start out with is writing down my givens. So I'm going to start over here and write down N1 equals 6, X bar 1 equals 7.6, S1 equals 2.36. Do the same thing for the second sample. N2 is 8, X bar 2 equals 9.8, and S2 equals 1.28. They also tell me the alpha level is going to be 5%. So if the production manager thinks that the two times may differ, he's going to start out with a null hypothesis, HO, mu1 equals mu2, HA, the two-sided alternative, the two times are different, where mu1 is the production time for model A, and mu2 is the production time for model or for design B. And ditto marks are acceptable. Now the next thing we need to do is talk about what? Assumptions. So let's talk through them first, and then we can all write them down together. What are the conditions that we need to work this problem out? We need an SRS. So what is it that needs to be an SRS? These workers, the 6 workers using A and the 8 workers using design B, those need to be a random sample of workers. In other words, it's obviously a problem if I put my best 6 workers on A and my slowest 8 workers on B. That would be a problem. So those workers need to be a random selection of workers. What else? Normality of what? Okay, so are my sample sizes big or small? Small. They're both small. I got a size of 6 and a size of 8. So one of the things we've learned is with this small distribution, I need those distributions of 6 and 8 to be pretty close to normal with no outliers. Now, sometimes you can check it, but you can't check it here because you don't have the data. So you're just going to have to assume that those two distributions, the one of these 6 workers and the one of the 8 workers, is pretty close to normal with no outliers. What else do I need? What's a key part of having a 2-sample problem? I need the 2 samples to be independent of one another. So we've got to have independence. And then it's not a bad idea to talk about the big capital N being more than 10 little n. So I could say that there's more than 60 workers I could have put on design A and 80 workers on design B. And so now we're going to write those things up and make it a little more formal. So here's what I've written for the assumptions, and you can pause this if you need to write stuff down. I will assume the workers in both groups are an SRS. Since my sample sizes are small, N1 equals 6 and N2 equals 8, I hope that the distributions are approximately normal with no outliers. I could certainly use more than 10 times 8 workers on each design, and I need the 2 groups to be independent. Some of you guys have the habit of writing your assumptions like this. The person who wrote it in blue here clearly gets it, or at least is able to explain it in a way that's much better than the red. The red is indicative of a student who memorized a bullet list and writes it down as such and hasn't figured out how to process the red into the blue. I'm up in the standards. The bullet points don't cut it. Now, I'm not opposed categorically to bullets. If you want to put little bullets on there, I have no problem with it. That's fine. But simply writing the red is problematic because you can tell as I ask you guys, what does this mean? You struggle on exactly telling me what it means because you don't know. You just have the idea that normal is important. What does normal mean? Something up there like normal or something. So I'm raising the standards a little bit. You're going to have to write a little bit more. So now I'm going to draw the graph, and I'll draw it in green here. This is 0. It's a two-sided test. And on this problem, these numbers that go right here and here are the difference in x bars. So if I looked at my two x bars, 7.6 and 9.8, if I subtract 7.6 minus 9.8, I get negative 2.2, and then the positive version of that is 2.2. That's what's going on right here. So really what I'm looking for is the probability that my x bar 1 minus x bar 2 is less than 7.6 minus 9.8. Or if you prefer to write it in the standardized form, it's t is less than, and I'll write the formula first. And then it's just a matter of filling in the numbers. So it's the probability t is less than 7.6 minus 9.8 minus 0 over 2.36 squared divided by 6 plus 1.28 squared divided by 8 square root. And I'll do the heavy lifting for you so you can just trust my calculations. This is t is less than negative 2.2 over 1.064. You might not actually write all this stuff down when you're working it. Depends on what it is you like to write down. And we're going to do this problem here with my green chart. Now, one thing I should point out is all I'm finding with these calculations is this area down here to the left. To make sure that I get the entire p-value, I actually have to double all of this stuff. Okay, so looking at the chart, and for this problem, I'm going to use the conservative degrees of freedom. So if I use the conservative degrees of freedom, I'm going to take the smaller sample size, which was 6, and subtract 1. So I'm going to use 5 degrees of freedom, which is t sub 5. When you're doing this on a test, somewhere you have to have the degrees of freedom written. You can have it written like we've done here, or you can have it written like we've done right here. But you've got to write on there where the degrees of freedom fall. Now, looking at my green chart, I go to 5 degrees of freedom, and I'm going to slide over on that row until I find 2.067. So that would fall right in here, which means that my p-value falls right in between 0.025 and 0.05. And that's just for the left side. So as I write this up, it's really 2 times a p-value between 0.025 and 0.05. So my actual p-value is really between 0.05 and 0.10. Now, earlier in the problem, they told me that alpha was 0.05. So what kind of conclusion am I going to make? I'm going to reject HO. And the other standard that I'm increasing, one standard was the conditions. The other one is I've got to see linkage. I've got to see a connection between this sentence and your conclusion. So what I'm going to write here is since my p-value is greater than alpha equals 0.05, I will fail to reject HO in favor of HA. I fail to reject because my p-value's bigger. That is, I continue to believe the design times or the designs take an equal time. Now let's look at question number 2. It says, do students at four-year universities work harder than those at two-year junior colleges? To help answer the question, we selected 27 random university students, 21 random college students, and they were asked how many hours a week they spent studying and doing homework. The results are shown below. Alpha level is 0.02. So for some reason in the summary statistics, they didn't write 27 and 21. I'm going to add those on here. And the first thing I would do if I was working the question is to write down my HO and HA. So here's what I come up with. The null hypothesis, the two groups study the same amount of time. The alternative hypothesis, university students spend more time than college students. And mu1 is the average study time for a university student. Mu2 is that for a college student. The next thing that I'm going to do is go through and talk about the conditions for each one of them. So like before, let's talk through the conditions and then we'll write them up. So what's the first thing? We need to have an SRS. They told me that they were randomly selected. That's great. I hope that random selection was like an SRS. So the students need to be randomly selected. Great. What's another thing? What is that? What does normality mean? For this problem, how do I apply that normality condition? Do I have a small sample, a medium sample, or a large sample? Okay, so these individual numbers are medium. Now it turns out, and we'll talk about it next week, but I can almost combine those two to get even a bigger sample size in my mind. But for right now, we'll say those are medium sample sizes. So what do the distributions of those numbers need to look like? As long as they're not really skewed, I'm okay. They don't even have to be close to normal. They just can't be too skewed or have outliers, since my sample sizes were medium. What else do I need? There's one other really critical component. The two groups need to be independent. So in this case, a violation of that might be if these guys live together. If these 21 or if some of the college students lived with some of the university students, then that would violate the idea of independence. And then it's a good thing also if I have at least 270 university students and 210 college students. Clearly that idea is met. So now we want to write all that up. So here's what I wrote down. Thankfully, the samples were randomly obtained, hopefully by an SRS. Since my sample sizes are medium, there's my numbers. I'm okay, provided there's no strong skewness or outliers. And certainly there's more than 270 university students, 210 college students. Finally, I hope the two groups are independent. So now we're going to come up with the graph and the mathematics. So my curve here looks like this. It's a one-sided test this time on the greater than side. And the number here is the difference in the two groups, 27.6 minus 19.3. Again, I'll use the conservative degrees of freedom for this problem, which gives me 20 degrees of freedom. So now I start showing the work. I want to know the probability I get a t bigger than 27.6 minus 19.3 minus 0 over big square root 4.83 squared over 27 plus 4.02 squared over 21. Once again, I'll do the heavy lifting, but you should probably practice typing into your calculator at some point. It's not hard, but it's easy to make a mistake on. And what I want to do this time is sort of a hybrid between the chart and the calculator. So we're going to take that t-test statistic and use the calculator to do this function. TCDF, lower bound, upper bound, degrees of freedom. And this will find the actual p-value which is something like 1.24 times 10 to the negative sixth. Okay, so now this small p-value tells me to reject HO. So I'll write since p is less than alpha, which means 0.00001 is less than 0.02, I will reject HO in favor of HA. I find great evidence that university students study more than college students. Now, I want to make a crucial distinction between what I wrote and what I didn't write right here. How's that grammar? What I found with this small p-value is really, really, really strong evidence that university students study more. I did not find that they study lots more. I found lots of evidence, but I didn't find that the difference was a lot. That's a different test. Do you guys see the distinction? I found a lot of evidence that they study more. How much more? I don't know. That's not what the test was finding out. So to analyze the how much more question, I'm going to use a two sample t interval on my calculator. So grab your calculator and go stat test two sample t int and type in the stats from this problem. So you type in that stuff. We'll just use a 95% confidence interval. That's fine. I don't pool, and I hit calculate. And hopefully your calculator will work better than mine. All right, here we go. So I'm pretty sure, I'm 95% sure that the true average difference in study times is in that interval. And notice calculator used 45.75 degrees of freedom. So I'm pretty sure, I'm 95% sure that college students on average spend between 5.7 and 10.9 fewer hours a week studying than their university friends. So that's how much different they spend. The hypothesis test told me I was really sure it was different. The confidence interval is telling me how different is it. I think that difference is somewhere between basically 6 and 11 hours different. And there's the first two examples on this sheet. Go through the third one in a bit. Problem 3 says a chicken farmer who supplies an international fast food chain is experimenting with ways to make chickens grow faster. His latest scheme is to remove the feathers from the young chicks so that the energy normally used to grow feathers will be used instead to make their bodies grow faster. In order to test his theory, the farmer takes 20 young chicks and removes the feathers from 10 of them. He then treats them exactly alike for 2 months, at which point he measures their weight and calculates their percentage weight gain. Can we conclude from the statistics below that the scheme was effective at the alpha equals 0.05 level? And here's the information from the feathered chicks and the defeathered chicks. So first, my HO is going to be that the two means are equal versus HA. The weight gain for the defeathered chicks was greater. Next, we need to go through and talk about the conditions necessary for the test. So I'm hopeful that the two samples were in SRS from their respective populations. Next, since we have two samples of size 10, we can combine those and treat it as a medium sample size. And with a medium sample size, I need to assume that there's no strong skewness or outliers. Finally, we need to make sure that these two groups are independent. Some of you will also want to write that we need to have at least 100 feathered chicks and 100 defeathered chicks, and that's fine. You could include that as well. Next, I'm going to go through my graph and calculations. So I've got the t-distribution. And when I subtract these two x bars, 112.5 minus 102, I get 10.5. So this one-sided test right here is 10.5. This is 0. And as I show my work, I want the probability that t is greater than x bar 1 minus x bar 2 minus mu1 minus mu2 over the big square root of s1 squared over n1 plus s2 squared over n2. And as I plug things into my formula here, that's going to be, let's see, I'll do this on the next line, I guess. $112.5 minus 102 over big square root. Now notice this, a little tricky. That was S1 squared is 98.6. So S1 squared is 98.6. Be careful with that part. Over 10 plus 79 over 10. It was already squared in what was given. Now what I'm actually going to do on this one is use the calculator to do all of the work. So I'll pull my calculator up. And I'm going to do the 2-sample t-test. I've got the stats that I'm going to type in. And when I get to s of x1, notice I don't have s of x1, so I'm actually going to type in the square root of 98.6. It'll calculate that for me as it just did. N is 10, x bar 2 is 102. Again, I've got to do the square root of 79, and N2 is 10. It's the one-sided greater than test. We're not pooling. And when I calculate it, it'll give me my t-test statistic as well as my degrees of freedom and my p-value. So I'm going to take advantage of this and add the degrees of freedom on here so everybody will know what I'm using. 17.78. And then I can write all this stuff up. So this is the probability that I would get a t greater than 2.49, which gives me a p-value of 0.0114. If I was using my chart, just in case somebody was doing this on their chart so you could see how it would compare, I'd still have the probability t is greater than 2.49, but using the conservative degrees of freedom, I would use df equals 9, and I'd get that the p-value is between 0.01 and 0.02. Or if you use the tcdf function on your calculator, you'd get 0.017. And you can see that these numbers are pretty close to one another. And in any case, with a 5% significance level, all of them are going to result in the same conclusion. And so now we need to write that conclusion. Since my p-value is less than alpha, so I'll write on here 0.0114 is less than 0.05, I will reject HO in favor of HA. That is, I no longer believe the average weight gain of the chicks is the same. I now believe the defeathered chicks, got an E, defeathered chicks gain weight faster than their fine feathered friends. And so there's 3 examples of 2-sample T procedures. one with a chart, one with a mixture of the chart and the calculator, one with the calculator, and we also talked about a confidence interval back on problem number 2. There's a